Hello everyone, welcome to this one-shot review of Unit 6, Integration and Accumulation of Change. And this video will cover both AB as well as BC topics. And yes, I will be covering the key concept and I will break down the subunits as usual. And we will be tackle some problem solving techniques here. So let's get into this. Right. So this is all about we are stepping into the integration, and it depends upon the basic idea is accumulation of change. And the differentiation is about rate of change, right? So it's accumulation of change. Let's understand it. So the concept of accumulation of change is about understanding how small changes add up over time to create a bigger change, right? We will be adding up the small changes and that will give a, like we will be summing up those small changes that will create a big change. Now, a very simple example. Here you have a jar and the water is dropping like this, right? This much filled at 1 second and this much filled this, like it is had been. So it is getting accumulated when you, the drops are getting, so when you want to find the full volume of the jar, like that is what accumulation of change. At every time, there will be a changing in the droplets and it will increase the volume. So this is the concept of accumulation of drops over a time, right? And we're going to understand this thing as a function. The accumulation of change is a function, and that's the basics of integration too, right? So here a basic question. You are on a road trip and have your car on cruise control for 4 hours. You travel at 60 miles per hour. How far have you traveled? And this is the graph. And without graph also, you can easily say that, right? So you have the control for 4 hours. You travel 60 miles per hour. How far? The distance is speed into time. So you have traveled 240 kilometers. Just you will product that. Now let's understand this graphically. This 240, if you interpret in a graphical form, it will be like this. So 60 kilometer from start till 4. That is a curve, like constant speed we are going. So we want to, if you find the area between the starting and you're ending at 4 hours, right? What is the area? It's 4 times 60 is the width, so 240. And accumulation of change is connected with area under your f of x, your graph, right? So it's not every time like this simple. So you might get something like this. And yeah, if you want to find the speed or if you want to find how far you have traveled, so accumulation of change will help us. And this time it's not easy. This is easy, but this is not easy. And yes, integration will help us in this complex stuff. That's all about the entire unit. And now, 6.2, approximating areas with Riemann sums. Okay, so previously we did area under a curve, right? So we have some techniques which is called Riemann sums, and let's understand. First, area under a curve means it is between your x-axis and your curve. So this area is what we mean, area under a curve. Now, second case, if you see area under a curve, doesn't means you have to go. No, it is not. Right? So area under a curve is between x-axis and your actual graph. So this is my graph and x-axis is here. Now, we still call it as area under a curve, but it's not like it's real. Actually, it's underneath, right? And here, area under the curve, area between curve and x-axis, area between curve and x-axis, area between curve and x-axis. So these are the three cases you can spot, right? Now, here we have a curve and you want to find the area between A and B. Basically, you're finding accumulation of change, area under a graph between x-axis and the curve. Okay, how should I do this? Right? So let's understand it step by step using Riemann sum. Actually, the basic idea is we will make into rectangles. That's the idea. For example, you make a rectangle over here and rectangle over here, rectangle over here, like smaller rectangles. And in this way, we will find area of rectangles and then we will find the approximate area. We are going to approximate using Riemann sums, right? Now, we have steps. Break the intervals into subinterval with equal width, and it's very important, equal width, and we are going to call it as del x, right? So for example, if it's 1 to 10 and you have to divide it into 5 intervals, each interval it will be 2 units of width, right? So it should be equal width and it is called del x. We have a formula to find the del x. So AB is your interval and you want to divide it into some n, maybe it's 10, 100, whatever. Del x is b minus a by n. Okay, this is the first step. Now, step 2. For each assignment subinterval, you have to draw a rectangle whose height is determined by f of x. Yeah, at the first step, we got the width, right? But height of the rectangle, if you want to draw the rectangle, you need a height. Height is determined by f of x. How? Let's see this. So there is different ways to choose height as per the Riemann's theory. So first one is left endpoint, right? So if this is your curve, right, and you want to draw a rectangle, I have choose, so this is your interval 0 and 1. This time I choose the right endpoint. I make a rectangle, right? If you choose a left endpoint, like it will be something like this. Left endpoint over here. Left endpoint, and I'm making a rectangle like this. Anyways, we are making rectangle, but there is different ways to choose. Left endpoint, and one more is there, which is right endpoint we have seen, and the midpoint. Okay, what if I choose the middle point? Yeah, we can do middle point also we can. So the height, choosing the height matters, and left endpoint we call it as left Riemann sum. Right endpoint we call it as right Riemann sum, and midpoint Riemann sum. So these are the three things we can do here. Now we will be seeing that one by one. And next, after choosing height and drawing rectangles, calculating the Riemann sums, just find the area of rectangles. That's it. Area of one rectangle we know, like the breadth into height, right? The width. So here our breadth is along x-axis, it's del x. And your height is, it depends upon which interval you're working on and which point you have chosen. For example, if you're working on the second interval and you have chosen left Riemann sum, so second interval is like if it is 2, 4, right? So you will be plugging in 2. The width is going to be the same, like 2. And left means f of 2. That's simple. And if it's right, this will change. Midpoint 2 and 4, midpoint is 3. So that is how this formula will work, right? Now f of x is the height of ith interval. So for each interval, this value will change the height, but del x will remain the same since we are working on this. And now area from -1 to +1. So -1 to +1, what is the area, right? So we need to find this area. And the basic approach will be like this. You will find the del x, b minus a by n. I'm working from -1 to +1. So 1 minus of -1 by 4, it's 1 by 2. Now, once you got your del x, and how many interval I'm dividing, actually, I have mentioned 4, right? So in this case, we are dividing into 4 intervals. So the intervals will be like this. -1 to 0.5, negative 0.5, right? So 4 intervals we did. And you just write the interval. Then at every interval, you will work on the area, right? I'm not doing this here. The same example, I will explain you with many different rules. So this is the basic idea over here. And let's see this. Here, I'm going to show the Desmos so that you will get an idea to solve this. Here we go. Right. So f of x is minus x squared and -1 to 5. So some limit is there. So accumulation of change, the Riemann sum, we are finding that, right? It's nothing but integration. So if you change the limits -1 to 1, you got something like this, right? So basically it will add up all the values. it will make rectangles and simplify, right? This is how it will work and moving forward. So the accumulation of change as an integration. This is the basic idea over here. But yeah, we will see how these notation comes and all. Moving over here. Left Riemann sum. Same del x will be same whatever sum you're doing. So del x is here. We need to find area of the this thing between x and y. So we need to make rectangles, and we are making 4 rectangles over here. If you make more number of rectangles like subintervals, you will get more approximate, like a better approximation. So del x is, we just apply the formula, we got a 1. And area is, for sure 1 is there. So 1 times, only the height will change. So you just add up those height. So here, the height is going to be, let me take different color. First height, I am using left Riemann sum, and you're solving area from 0 to 4. Okay, we are finding area from 0 to 4. And first rectangle I will be drawing over here, and it's a left Riemann sum. So my rectangle should go like this. I'm choosing a left point. So in 0, 1, I will be choosing 0. And yeah, it says 1. The height is 1. Then, and next interval 1 to 2, 1 will decide what is my height. So you just go to your graph. That's it. You choose the point 1 and go to it, and then complete a rectangle. Now this determines is 4. Then from this, you have to go here and you go outside. Even if you go outside, it is not a problem. Just make a rectangle of equal width, 2 to 3. 2 determines the height. Actually, it's 5. So it's 5. And again, here we go. This determines the height, and it's 4. And approximately it's 14 square units. This is left Riemann sum. And right Riemann sum, it's exactly same. Find del x and then area is this. How I got it? Same. 0 to 1, 1 to 2, 2 to 3. 4 equal rectangles, 4 equal subintervals we did. Now, 1 will, 0, 1, 1 will decide the height. So this you have to raise, and you will be going here, and this is a rectangle. These are the errors, right? And 1 to 2, 2 will decide the height. The right endpoints will decide the height, and this will be something like this. And 3 will decide the height, something like this. And 4 will decide the height, something like this. Right? And we got the same 14 actually here. Now midpoint Riemann sum. Midpoint will decide the height. So 0 to 1, 1 to 2, 2 to 3, 3 to 4. Midpoint is half, right? This will decide the height. So from here, you need to go to the graph. And then you just make a rectangle out of it. That's it. Then here you have to move to the graph, like go straight and make a rectangle. And here you can go this mix. And between that, the graph is over here. Since it's a parabola, we got a symmetric values, the rectangles are. But yeah, some difficult graphs also will be coming. So del x is same, and area is finding this. We have approximated, it's around 14.5. And there is one more rule. It's these are the 3 are Riemann sums. Now there is something called trapezoid rule. Of course, you might have think, what if to avoid the error? So I'm making something like this, and here, if I make a trapezoid, there will be, these errors can be avoided. If I make a rectangle, they will be errors. So yes, that is something called trapezoid rule. And trapezoid rule, there is a slight change over here. So del x is b minus a by n. That's the same. We are dividing into subinterval. But area is sum of the two f of xi. Both of them will determine the height. This also will take a height. At 1 also will take a height. Right? Height means I'm taking the parallel base, right? For a trapezoid. And the width. So f of xi plus f of xi plus 1, 0 and 1 means both you will apply and add and divide by 2. Like you are taking average of it times the width. This is the concept. And so here we got, okay. So the better way to do is, let me show you. So del x by 2, anyways, it's going to be del x is fixed. And only this will change, f of xi plus f of xi plus 1. This will be changing. If you take the first interval, it's f of 0 plus f of 1. Then for the second one, it's f of 1 plus f of 2. F of 1 plus f of 2. And next one, it's f of 2 plus f of 3. And next one, it's f of 3 plus f of 4. So we notice one thing. The very start ending point and the final, the very start and ending extremes will come only once, and all the other stuffs will come twice, right? So it's, you can write f of xi, x1 plus whatever comes will come 2 times. Then f of xn will come only 1 time, right? x2, f of x2, f of x3. So we will apply that, and this is what area is half into first one, which is f of 0. This is, and f of 1 will come twice. This will be acting in this trapezoid, also in this trapezoid, right? That's why. So 2 times of that height is 4, and 2 times 5, 2 times 4, 1, and you just approximate, it's 14. Mostly we got 14 for the same problem. So yeah, it will be close to 14, but it's still an approximation. And trapezoid estimation, when your curve is concave up, your estimation, like it's overestimate or an underestimate. Okay, if you're finding area from here to here, draw a trapezoid. For sure, it will be out of the, like, area under the curve is, this is what I need. I have some little above that, right? Let me check for a clear visualization. No, yes. Yes. So this point with this point, and you make a trapezoid. Actually, I need only this area. So when you're working for a concave upward graph, there will be an overestimation. And concave downward, it's an underestimation, because this is area under the curve we need. Actually, this area is covered, but this is missing out. So we are underestimating over here. Right? And moving to next, Riemann sums, summation notation, and definite integrals. We have seen Riemann sums, right? Now, summation notation for the Riemann sums. First, the area under the curve of f of x on a comma b is represented by this summation form. Summation means is like adding up something, right? So we are dividing the given interval into small rectangles. So k is equal to 1 to any number that we are wishing for. And del x times f of xi, and this is crucial, right? Because it depends upon whatever we are working. So we change everything in a, b form. So del x is b minus a into n. And for this, it's not just f of xi, a plus b minus a by n times k. So k is in which interval you are working. So a plus the del x into k, right? Then, and area under the curve means we want to make so many infinite number of rectangles so that we will get the best approximation, not 10, 100,000, like many. So limit n tend to infinity. K is from 1 to n, and n tends to infinity. It's a very big number. So many rectangles, so many slicing we are doing here. So this is the area under the curve in summation form, right? Now let's understand for each. Left Riemann sum with sigma equal to 1 to n f of xi. You know the formula, but just make a sigma, like, which means same formula we will be repeating for every interval. First interval, it's 1. Second interval, 2, in that way. Right? For the right Riemann sum, I will be not choosing the first endpoint, right? If it's 0, 5, I will choose 5, right? So the right endpoint denotes xi plus 1. And midpoint interval, the midpoint of those values, xi plus 1 by 2. 0 plus 5 means I will be plugging in 2.5 here. So that's it. And in all the cases, the limit del x tends to 0. right? Del x tends to 0 means you are making a width of like this. This is your del x means imagine how many rectangles you need to make. So n tend to infinity if you say, or if you say del x tends to 0, we are trying to convey the same thing. You are making the width so much small means number of rectangles will increase, right? So limit del x tends to 0 in all the cases, or you can say limit n tends to infinity, right? Now integral notation, coming to the integration part. How to write this in integration? It's a very short form, and this is what a curve. And for this, you have to mention integral sign a to b f of x dx, whichever function we are integrating and within the limits. So this entire thing, the integral notation will go. And this also we call it as definite integral. And we will see some other integral types also. And this is the area under the curve in integral form is this. Now, the fundamental theorem of calculus and accumulation of function. We have two fundamental theorem of calculus, which is FTC, for accumulation function and for integrals. So let's go. We know now integral a to b f of x dx means what I mean? I mean area under this curve from a to b. Now, the area under the curve f of x on this closed interval. What if you don't know the endpoint? Okay, from A to B, this is what if the ending point is not known by you? So in that case, we denote a capital F of x, which is accumulation function, integral A to x, of course, f of t dt. It can be any variable. It's not like time or something, right? So this is the way accumulation of function will be written. Now, fundamental theorem of calculus, let's connect. If A is a constant and F is continuous, then do you remember accumulation function can be written like this, A to x, f of t dt. Now, if you derivate this like d by dx, you got this. Actually, what should I got? I should get f dash of x is d. But the fundamental theorem says it will give you back the f of x. If you differentiate the accumulate function, it will give back the original function, right? So what we can understand, the differentiation and integration got cancelled, something like that, right? So when two things plus minus will get cancelled, like multiply 3, divide 3, they will get cancelled. So inverse operation will get cancelled. And yes, derivative and integration, they are inverse operations. And we are going to call it as antiderivative, right? So derivatives and integrals are inverses. F is a derivative of f of x. Like if you derivate this, f dash of x means its original graph. And in this case, f of x is the antiderivative of the capital F of x is antiderivative of f of x. Right? Okay, let's go. There are some, that is the basic one. Now, what if I have a to some function, not just x, like x cube, x cube plus 5, something like that? Very simple. How to solve this? Imagine the chain rule. So what we did, d by dx of integral a to x f of t dt. You plug in x, that's it. F of x dx and d by dx will get cancelled out. But instead, other than x, if you have this, yeah, again plug in the same f of gx and apply the chain rule. G of x, when you differentiate, like whatever inside, you will differentiate g dash of x. Another case, both are like h of x to g of x. Again, you will apply this f of g of x, g dash of x minus f of h of x, h dash of x, right? And a simple example, f of x is given. We need to find f dash of x. So we know f dash of x is equal to, that means d by dx, right? It will undo the integration. So f dash of x is sine x cube. This will get cancelled, and whatever the number you can ignore. So sine x cube times, it's not just x, right? So you have to do this 3x square sine x cube. This is the connection in the FTC, the first accumulation of function and the derivative and the integral. Okay, here is the solution. You can see that simple it is. Now, interpreting the behavior of accumulation function involving area. Accumulation is also a function, and we are going to interpret the behavior. It's very simple, where it's increasing, decreasing, concave up, concave down, maximum, minimum, inflection. We already did this in our 5th unit, right? So same thing. Accumulation function is this. Don't forget it. This is the first FTC. And derivative of accumulation will give original function. If you derivate this, it will give you the original graph. Now, f of x is increasing, like accumulation function is increasing, means whatever the function is increasing, f dash of x, that derivative should be greater than 0. But I want in the function form, not like f dash of x. So there is two choices, or f of x, because f dash of x and f of x are same. So same, and f of x is decreasing means, of course, f dash should be less than 0, or f of x should be less than 0, because they are same. F dash of x, like capital F dash of x and f of x, they are equal, right? And relative maximum, f dash of x, like this accumulation will change from positive to negative, or the original function changes from positive to negative. Same thing for minimum, negative to positive. It's exactly the same, only you should be able to connect them, the capital derivative of accumulation and the original function. They are interrelated. If you know that, then it's very simple. Now concave up, f double dash will change the sign, which means f double dash will be positive concave up, like as an accumulation. The original function's derivative should be greater than 0. And concave down is less than 0. Now point of inflection, second derivative of your accumulation function should change its sign, or first derivative of original function should change its sign. Now let's see a simple problem here. Given the graph of f and f of x is 0 to x f of t dt, and f of t is also given, analyze the behavior of f of x. Okay, this is what? F. And f of x is accumulation function. Capital F of x is increasing. Like accumulation function is not here. If it's given, I will say, okay, if your accumulation is like this, I will spot it. But how can I interpret? So apply the rules. F of x should be greater than 0. F of x positive means for what values it's above x-axis. Right? From this to this and this to this, it's above x-axis. So it's minus infinity to this value, it's 2. And union 2 comma infinity. And in decreasing, f of x less than 0 below y-axis. Right? And we got these intervals. That's simple. Now, relative maximum. F of x has relative maximum when f changes from, like, original function changed from plus to minus. And relative minimum if it's minus to plus. So this is my original function. From plus, it's plus to minus. Here there is a change. Then draw a minus and there is a change. So it is minus to its maximum, plus to its minimum. Right? So now concave up, we need f dash, right? So I have taken an f dash of the graph. So concave up, if your f double dash is greater than 0 or f dash is greater than 0, this is f dash. F dash will be greater than 0, or even if they give the this kind of graph, you will able to find that. Just find your tangent greater than 0. Positive tangents. And where it is greater than 0 means above x-axis from 0 to infinity, and concave down for minus infinity to 0. Now point of inflection, where f dash of x changes its sign. So it's minus to plus. Here is a change in sign. So at x is equal to 0, there is a point of inflection. That's simple. Now 6.6. Applying properties of definite integral notation. We have so many properties. First is zero with interval. So a to a, it's same interval means it's 0. no area will be there, right? And constant multiplication, a to b, k into f of x means, yes, you can take the constant outside and you can only work on the function. Now, reversal of limits. A to b f of x dx equal minus. So if you want to reverse the limit, yes, you can do. You can switch it, but a minus will come out. You have to multiply a minus. An adjacent interval, a to c f of x, c to b, same function. You're finding separate areas. You can just make into a single area if they are adjacent. There is no gap at all. Now addition, a to b f of x plus g of x dx. You can apply the integral for each terms, right? And subtraction also same. You can apply the integration for each term. Symmetry in the interval, minus a to plus a. So yeah, minus a to plus a. They are symmetrical. About the line of symmetry will be at 0. So it's just same area appear twice. So twice 0 to a you can change, right? Same area will come. Now, fundamental theorem of calculus and definite integrals. Okay, for accumulation, we have seen a FTC, fundamental theorem. Now for definite integrals. If f is continuous on a comma b, then integral a to b f of x dx. Okay, I know this notation, but how I will be solving? You just take, what is this f of b? If it's your f of x is antiderivative. You take antiderivative and apply your upper limit and then minus apply your lower limit, right? We will see how to find this f of x to capital F of x also. This is the FTC for definite integrals. Now finding antiderivatives. Of course, we need antiderivatives and we will see in definite integrals, basic rules and notation. Okay, what is antiderivative? If f of x is x square, f dash of x is 2x. So what I will say, 2x is derivative of x square. Now you just switch it. X square is antiderivative of 2x. Got it? So they are like inverses, I said, right? In the same way. Now, antiderivative of f of x, usually we will denote it by capital F of x. It might be confusing, but yes, if you practice and you should be more keen and focused when you're solving, even a little change in the capital F, small f, you will get confused, right? So pay more attention. And what is an indefinite integral? Indefinite integral represents collection of all antiderivatives of f of x. So this is your f of x. And if you find antiderivatives, it's not just a unique one. It have infinitely many. And indefinite integral will give you every possible antiderivatives of your function, right? So integral f of x dx equal to f of x plus c. Plus this constant will decide the family of functions. And f of x is antiderivative. C is a constant of integration. For example, we said x square is antiderivative of 2x, right? Because 2x is derivative, we just switch it. X square. 2x is also, let me write. It's not only derivative for x square. 2x is also a derivative for x square plus 3. Then what I say? X square plus 3 is antiderivative of 2x. Yeah, you can just change the constant. So there is many possibilities here. That's why we introduced this special. This is called integration constant. And f of x is x power n. Antiderivative. If you derivate it, f dash of x. Now, f of x is x power n. Antiderivative, like what you did, you multiplied an n, you subtract 1. Here you will do opposite. You will add 1 at the power and you will divide by that value. And we have many more. Integral e power dx is e power x plus c. And the constant of integration is must when you're doing improper. There is no limits in improper. Okay. A power x dx equal to a power x 1 by ln a. you can connect every rule of integration with differential rules. There is a slight change, either it's a reciprocal something, and this constant will be always there. And 1 by x is ln modulus x. For trigonometric, these are the formulas, right? You can easily connect derivative of cos x is minus sin x. Derivative of sin x is cos x. Now integration of cos x becomes sin x. So we can just relate everything with differentiation rules. And inverse trick also same. Derivative of sine inverse x is this. Derivative of secant inverse is this. Derivative of tan inverse. Now integration of this thing will result in sine inverse. Like it's very simple. If you change this, it will become integration with a dx. D, when you transform the equal sign, it will become integral and dx will come over here. Then sine inverse and mandatory C. Same thing. So by practicing, you will be familiar with these notation and you will quickly see when you see this, oh, this related with sine inverse. You will get that. Now 6.9, integrating using substitution. Okay, these are techniques. It's not every time it's so simple. There will be some complicated and we have some methods. Substitution rule is simple. We are going to call it as U substitution. And U equal to G of X, where G of X differentiable function, then the derivative of U is du is G dash of X. So there will be some complicated stuff. And we will take one as a mu, then we will derivate that. U is G of X means du is G dash of X. And G of X must be a differentiable one. So if the integral involves G of X and its derivative, so when I can apply, if your integral have G of X, also its derivative seems to be there in that integrand. We call this as integrand. Okay, this is integral sign. Yes, then you can able to use this U substitution. Okay, so this is the way and rule. So step, it's very simple. Identify the substitution. Okay, what is my U? That is important. So look for a part that can be set as U. Typically, a function whose derivative also appears in the integral. Okay, so for example, you got an x square and the sine x square, like kind of a 2x. Okay, then I will say, okay, x square's differentiation is also there in the integrand. So I will choose this as U. Right? That's the simple and important part. And substitute. Okay. So after finding U, find du in terms of dx. Right? So now you will change everything into U form. No dx, no x here. So simplify the integral and write in terms of U. And then integrate with respect to U. Once it's solved, replace the U with whatever the function of x. That's it. Here a simple thing. 2x into x squared plus 1 the whole cube. Okay. This is having its differentiation is there outside. So U will work. First, you decide what is U. X squared plus 1, don't take the cube. Right? Only this we are taking. And du is 2x dx. Now, write the function. Integral 2x is equal to integral. This becomes U. So U cube. And 2x dx can be replaced with du. That's it. And this integration is simple. This is called power rule. You will add 1 at the power and that result you will divide. So you power 4 by 4 and make sure you're adding constant of integration. That's it. Now you have to replace back. You simplified it. No more integral sign. Now substitute back. My u is x squared plus 1 and x squared plus 1 the whole power by 4 plus c. Right? Now 6.10. Integrating function using long division and completing square. Okay, these kind of stuff I have. Right? And in this case, try to divide when your numerator is, degree of numerator is bigger than degree of denominator. Just go with polynomial division. So if you divide, I will get quotient as this and remainder as 11. Now, this given integrand can be split into your quotient plus remainder by divisor. Right? We have written it. Now, apply integral. And you can apply the integral for each term as I have said. You can do that. Right? So through 3 x square if you integrate like power rule in integration x power 3 by 3. 5 x power 1 power rule x square by 2. and 5 dx. dx will change to x. Okay, x. And a constant of integration. I'm just integrating the first part. Second is quite a different. I have the variables in denominator. So for this, we have a rule, ln rule. So you can again use the u substitution, because if you take u as this and du will be dx, yeah, that is there. So we can do that. And du is dx. So this is 11 by u du. And 11 ln, because 11 you take out, 1 by u du is nothing but ln mod u, right? So there is another constant. And you replace u with x minus 2. Now you combine those results, right? C1 and C2, they are anyways, they are a number. So you just make it a single C and combine all those terms. That's how the U substitution will work. Here, double U substitution over here, right? And 1 by x square plus 6x plus 10 dx. This thing, you can't divide, right? Numerator's degree is less. So, but try to make, if it's a complete square, we can apply. So completing square means take the one which you want to make it complete square, and x squared plus 6x. The coefficient of x you divide it by 2. It's 3. So add 3 square minus 3 square. Now the addition 3 square and the x square and x term will make a complete square. So this is your A, this is your B. And you have a middle sign as plus x plus 3 the whole square. And this, if you simplify, 1. That's it. Now 1 by x plus 3 the whole square plus 1. You apply the integration. Now, okay, so there is no rule. So you can use u substitution, use x plus 3 and du is dx. Yes, I have that. So replace, change everything into u. So 1 by u squared plus 1 du. Okay. So this you can relate with tan inverse of x is, like differentiation of tan inverse of x is 1 by x squared plus 1. Now I have this, which is an integration. So differentiation will be tan inverse of x, and here it's u, tan inverse of u plus constant integration, and replace your u with whatever you have taken, x plus 3. That's simple. Completing square also we can apply. Now it's time for BC topics. 6.11, integrating using by parts. Let's see. We have learned product rule in differentiation, right? When product of two functions is there, keep the first same, differentiate the second, plus keep the second same, differentiate the thing. Now, let's integrate on every part. Like I just did integration, and let's see d by dx, and this will get cancelled. Integration and differentiation, uv. And integral u, shortly I can say dv, v du. So, integral u dv is equal to uv minus integral v du. So, this is the by parts rule, right? Integral u dv equal to uv minus v du. Let's see an example. So u means what? U is a function that simplifies when you differentiate it. dv is a function that is easy to integrate. That is how you will choose u and v. So steps, identify u and dv from the integrand, compute du and v. Okay, because my formula have all this. U dv equal to uv minus integral v du. Okay, you will choose u and you will choose dv. From dv, you need to find what is v, right? And also whatever you need, you have to find that. And substitute in the formula and solve the remaining integral. One will be already solved, other will get simplified. So you will again, you can easily integrate, or again you have to apply the some of the techniques. Either it's u substitution or again integration by parts, whatever. Here is a simple example, integral x square sine x dx. Okay, u means easy to differentiate, right? X square, it will become smaller when you differentiate, but when you integrate this x square, it will become bigger. X power 3 by 3, like that it will increase. So u is x square and dv is sine x. It's not v, it's dv. So once you take your u, find du, and your dv is sine x. If you want v, you need to integrate. And it's minus cos x. We have those rules, and don't apply c over here. We will add it eventually. Now write the formula and plug in those values. uv. Your u is x square, your dv is sine x dx. Okay. And u is x square, v is minus cos x, minus in the integration, that formula itself, and apply those. First one is done. Second one is 2x cos x dx. Now, again, you can apply because substitution, I think it won't work, right? So, let's take this and solve this separately. My u is 2x because it will become simple when I differentiate, and cos x is easy to integrate. So, u is 2x and dv is cos x dx. And du you find from this, integrate and find v. That's it. Now, uv rule, again write the formula. U dv equal to uv minus v du. Apply all those you got. This is what we will get. And now integration of sine x is simple, right? Cos x plus c. And that's it. You can just merge those two answers, minus x squared cos x plus this stuff and the constant of integration for all stuff together, right? And that's the integration by parts. Now again a BC topic, integrating using linear partial fraction. You might have learned this in your pre-calculus journey, but let me explain you in a simpler manner. So first, partial fraction decomposition. How to do that? Factor the denominator, first of all. And you have to factor it completely into linear or reducible quadratic factors. And set up the decomposition. So I want sum of the fraction, like not like x square plus 4x plus 4. I want 1 by x plus 2 plus 1 by something like this, linear and sum of the fractions, right? Now, for linear factors like x minus a, use a by x minus a. Linear factors will repeating like multiplicity, you will use this. There will be different coefficients. So if it's x minus a the whole cube, I will write a1. I don't know the coefficient. We need to find it. a1 by x minus a plus a2 by x minus a the whole square plus a3 by x minus a the whole cube. And after finding a1, a2, a3, we will be completing the decomposition. Now, how to solve for coefficient? There is different ways. You can multiply through by the common denominator to eliminate fraction and solve for unknown. One by one you can find. Mostly we'll get 2. And yeah, there is many ways we can solve. Then after decomposing, you have to integrate each term, each fraction kind of stuff separately. And there also you might apply different techniques. So here is a quick example. 1 by x square minus x minus 2. Yeah, first of all, we will think, okay, let's go with the complete factoring. Like what mean completing the square. Yes, you can. But I'm going to explain this into partial fraction. Factorize the denominator and you got this. First step done. Next, decompose. So 1 by x square minus x minus 2 is first coefficient a by first factor plus b by second factor, and we need to find what is a and b. How to find it? Cross multiply. Okay, if we cross multiply like this, a into left side will be same, ax plus a, and this will go bx minus 2b divided by these will get multiplied. This and this are same, right? So they will get cancelled and you got a simple equation. There is no x term in left side, so 0x, right? And ax plus bx, I'm just grouping x terms and constant. And you relate it, a plus b is x coefficient. Here x coefficient is 0. A minus 2b is constant. Here constant is 1. And solve for the simultaneous equation. Okay, here we can. I take the two equations and I'm going to manipulate those and solve for a and b. I'm just doing it quick because it's simple, right? I got this. Now you plug in those values into the decomposition and we got it. And in simplified manner, this is how it will look. Now you integrate it separately. Because if you make this linear, it's easy. I know that 1 by x is dx integration is ln x. So I can relate with that, right? And 1 by x minus 2 is also ln x minus 2. You don't want to apply u substitution. It's quite direct over here. So this is what we got. This integration, you do it separately. The rules allow us to do. And 1 by 3, this is ln x minus 2 minus 1 by 3 ln x plus 1. And constant of integration, you can simplify it further using the logarithm laws. And that's it. This is the answer. Right? And next one, evaluating improper integrals. Yes, we can evaluate improper integrals also using the limit concept. First, what is improper integrals? These are those integrals where the integrand becomes infinite or the interval of integration is infinite, the intervals. So it can be to infinity, something like this. Now, types of improper integral, two major types we have. Yeah. So types of improper integrals, we have two main types. One is infinite interval and discontinuous integrand. Right? Now, what is infinite interval? When one or both of the limits of the integration are infinite, like minus infinity to plus infinity or 0 to infinity, something like that. Discontinuous integrand means the integral of f of x, that a function will have some undefined at some point, right? And that will be in the interval of the integration. So that is discontinuous integrand. And here are some examples for infinite and here for this. So which means C is in my interval, but at C the function will not work. It is undefined. So this is discontinuous. And this is A to infinity minus infinity to B. These are infinite limits, but still we can evaluate. Let's see how. Now steps to evaluate improper integrals. Rewrite as a limit. So replace the infinity or the point of discontinuity with a variable and take the limit. And evaluate the integral, solve the integral as usual, and then apply the limit. That's simple. Okay, so it might converge to a finite value, or the final evaluation also can go to diverges, means it can go undefined. So here is a simple example, 1 to infinity, 1 by x squared dx, the first kind of improper integral. What is the first thing? Let me remove the limit as infinity part and make it b or something. That's the first step. Limit b tend to infinity. I change it, but I have to mention b means b is something which is tending to infinity, right? This is what rewriting it. Now, evaluate the integral. Okay, only the integral you take because it's a kind of definite integral for us now. So integral 1 to b. Okay, so just do this integration. Actually, the power rule will work here. X power minus 2. And yeah, power rule will not work for minus 1 only. Okay. So when you integrate this, you got this. And don't you see over here? Evaluate from 1 to b. What is evaluating from 1 to b? You need to plug in minus 1 by x. Sorry. 1 to b, and you just plug in those values. First, you have to give the upper limit, then a minus, apply the lower limit. And we got something like this. But what is b? So after evaluating, there is no more integral symbol. Now you reapply the limit b tend to infinity. Minus 1 by b plus b. So b tend to infinity means 1 by b will tend to 0. So just 1. So the entire the original integral form is equal to 1. Got it? Now 0 to 1, 1 by root x dx. This is 4. This is actually, it is improper, but still it's looked like a definite integral. But what is the problem? At 0 is we need to include, but that point your function will not work. It is undefined. So this is discontinuous integrand. And first thing, rewrite as a limit. Okay, how should I write? Where it is not working at 0. If I have root x minus 2 at 2, it won't work, right? So rewrite as a limit 0 to 1, this thing as something you change. This 0 is a problem, so you change it a into 1, and it's not exactly 0, but it approaches 0 plus, right? And evaluate the integral, this part alone, 1 by root x dx, and still you can apply the power rule because it's x power minus half, and you solve for 1 to a. It's same thing what we did before, and we got 2 minus 2 root a. Now you apply this limit a tends to 0 plus. It's very simple limit application. So you will get 2 minus 2, 2 minus 0, which is 2. Just you will plug in 0 here, and that will be eventually 0 and 2. That's the thing. Now, into the final part, we learned all the rules, techniques, the concept, and the evaluation of integral with accumulation function. Now, selecting techniques for anti-differentiation or integration. Okay, when to select what? And here is a quick review. So this is the first set is for both the students, A, B, and BC. And second is for BC only. Power rule, U substitution, long division, completing square. Power rule will not work for x power. Wait, let me take a different color. When it's minus 1, it won't work. But if you can make x power 100, yeah, you can make it x power minus 100 and you can apply U substitution. So it will be kind of a chain rule, right? So the differentiation of the thing should be there. Sine x square and 2x. The differentiation is there in the integrand. So that you can replace with U, right? Entirely will change into U, and then we will integrate, and then we will bring back that 2. And long division, when your numerator kind of a polynomial division, yeah, numerator degree greater than denominator degree means, yeah, still you can do that. And completing square, this also we can apply when we can't do long division, we can just check that. And BC only integration by parts, partial fraction, integrals. Parts means we have the formula. If you have something like U dv, okay, you choose U, which is simplified when we are differentiating, and dv is easy to integrate. Pick that and apply the formula. Partial fraction, decompose it, and then integrate it separately. Improper integrals, yeah, we have seen 2 types, and we need also seen the way and methods to evaluate it, right? And with this, I have given you the key ideas and key concepts with some techniques how to approach this unit, Unit 6. I hope this video might be helpful for you. So thank you so much for watching and giving the support. So if you really like this and if you find this helpful, you can share this with your friends and your AP Calculus students. Not only AP Calculus students, you can share with Calculus students also, right? So we will be curating some other video context also, especially on this one short review. So make sure you're subscribing, and yeah, so we'll be posting it soon. Thank you so much for watching. Yes, we have been into integration. And yes, we have the applications also and more on integration in next unit. Until then, keep learning and keep practicing. Thank you for watching.